Well, good evening, everyone. It is Wednesday, so of course it's time for a new live stream from Chem Help ASAP. So as you can tell from the title tonight, we are going to deal with some acid-base properties of salts. So first we're going to just talk about salts if they have acid-base properties, and if they do, can we determine if they're going to give or form an acidic or basic solution. And then we're going to take some salts that have acid-base properties and actually calculate the pH of a solution of that salt. So we're going to start low and kind of build up as we go. Now, in this live stream, I am going to be using equilibrium, Kas, Kbs quite freely. So that would be something that would be helpful to understand before you attempt these problems. Okay, but with that disclaimer being said, let's go ahead and jump into some of these problems. All right, so one thing I like about this topic is it can be very systematic. Like, I always enjoy it when there are a certain set of steps that I can do to get to the right answer. That's one of the things that I really love about chemistry and that I enjoy about math as well, as that systematic way of working problems. So you can see on the screen here, I not only have a nice table here at the bottom, but I also have a 4-step process to determining if a salt is going to change the pH of a solution. Again, we are just going to jump into this. And again, these first couple examples, we're just going to take a salt and then determine if it has acid-base properties. And then we'll talk about if it's an acidic or a basic solution. So I guess maybe the very first thing I should just do a refresher on is, what is a salt? And of course, a salt is formed when you have an ionic bond, when there's an exchange of electrons. So a salt will always have a cation, which is the positive ion, and an anion, which is the negative ion. So it's different from something that has a covalent bond. These are all salts. They have ionic bonds. Now, one really good way to tell if something is a salt is if it has a polyatomic ion being the key word there. If it's got a polyatomic ion, chances are you've got an ionic bond and you probably have a salt. All right, so that's just a little background. Let's talk about our rules for determining if a salt will change the pH of a solution. So first, I just want to quickly go through these steps. So the first step I'm going to do is I'm going to take the salt and I'm going to break it apart into its cation and anion. So I want to see how it dissociates in aqueous solution. The second thing I'm going to do is I'm going to take that cation and anion and I'm going to identify what I call the parent acid or the parent base of each of those ions. So each of those ions may be the conjugate of either an acid or a base, and I want to identify what those are. Then once I have identified that parent acid or parent base, I am going to determine if the ions themselves have acid-base properties. So I'm going to take that knowledge from step 2 once I've determined the parent acid or the parent base, and then use that to determine if that particular ion will have acid-base properties. And then lastly, once I have done that, I will be able to determine if a solution of this salt will give me an acidic pH, a basic pH, or a neutral pH. So with that being said, and all that foundation being laid, we are going to start with our first salt. And I should have, yes, I wanted to make sure that you could see the salt on the screen. Sometimes I forget that I put my face up here in the upper right-hand corner. So here is our salt, and we are going to go through each of these 4 steps, and we are going to determine if a aqueous solution of this salt will have an acidic, basic, or neutral pH. So let's go ahead and jump in. So my salt here is potassium nitrite. So again, the well, okay, so let's maybe first say, how do I know this is a salt? And of course, my key giveaway here is that I have a polyatomic ion. However, I also have a metal, and not that metals, you can have just pure metals, but oftentimes metals form cations. So that's another hint that you have a salt here, that you'll have a cation and an anion. Okay, so let's do our first step, and we are going to take the salt and we are going to dissociate it into the cation and the anion. So let's get my drawing pen up, and I'm going to have, let's start over here, potassium nitrite. So when it is in aqueous solution, i.e. when it's dissolved in water, it will form the potassium cation plus the nitrite anion. And you notice I've put AQ for aqueous. So also one thing I should point out is I'm only dealing with soluble salts here. So we're not talking about solubilities. We're only going to deal with soluble salts in this case. You notice for my cation, of course, it has a positive charge, and my anion has a negative charge, and I gave the proper charges for these as well. Okay, so now that I have identified the cation and the anion, I want to see if this cation and anion, what, again, the parent acid or the parent base of these ions could possibly be. So for potassium nitrate, I'm going to first look at the potassium cation right here. So maybe I'll just pull this out. So for potassium, again, this is where it's helpful to have some base of knowledge of at least the common acids and bases. You can have a table, or once you start to work with these, you can get an idea of just the most common acids and bases. So what I know about potassium is it does come from a parent base. It comes from potassium hydroxide. So that would be the parent base for potassium. Now, potassium hydroxide, when it is in aqueous solution, it will give, again, the potassium cation and the hydroxide anion. This is why it's a base. This would be an Arrhenius base because it is donating hydroxide anions. All right, so that's potassium. And now let's look at nitrite. Again, so I'm trying to think of a parent acid or base that would give me nitrite, and that would be nitrous acid. Now, nitrous acid is a weak acid, and actually, I want to be careful with this. I'm just going to be a little bit more accurate. You can write this without putting water in, but I like to put water into these equations. All right, so that is going to give the hydronium cation plus, I'm running out of space here. Here is my nitrite anion. So in determining these parent acids and bases, I have done something that I haven't actually explained yet. And that is I have already determined if they're strong or weak. So you can see with potassium hydroxide, I've only done the right-hand arrow. That's because potassium hydroxide is a strong base. So it is not in equilibrium, so the arrow only points to the right. However, for nitrous acid, that is a weak acid. So you see that I have equilibrium arrows here. That means you have a forward and a reverse reaction. Now, that is important because we want to make sure that we designate these as strong and weak, and if they're in equilibrium or equilibrium or not, because that is going to determine the acid-base properties of each of these ions. So, potassium here, because it comes from a strong base and there's only the right-hand arrow, that means the potassium cation will not go back to reform potassium hydroxide. So potassium cation is just not strong enough to remove the hydroxide anion from water to reform potassium hydroxide. Again, this is only the right-hand arrow. So potassium comes from a strong base, which means that it is not going to contribute any acid-base properties. So let me put this maybe in green here. So I'm on to step 3 here, determining if each ion has acid-base properties. And for potassium, I guess I'll just write it maybe over here. I'm going to write no to say it does not have any acid-base properties because it's coming from a strong base. Now let's take a look at nitrite. Again, this came from nitrous acid, which is a weak acid. That means it is in equilibrium. So what this also means is that you have the reverse reaction. So nitrite, the anion, does have a reverse reaction where it can take a proton from water or from the hydronium ion and reform this weak acid. So again, we have the forward reaction occurring as well as the reverse reaction occurring. What that means is this anion does have acid-base properties, so it will change the pH of an aqueous solution that it is dissolved in. So I'm going to go back here and write yes, that's kind of a funky E. So my potassium does not contribute anything to acid-base properties, but my nitrite, because it comes from a weak acid, does contribute to the acid-base properties of this salt. Okay, so what that also means is I can write, let me write the reverse reaction here. So nitrite, when it is in aqueous solution, can react with water. It is weak, it is in equilibrium, but it will form a little bit of nitrous acid, and that would leave a little bit of hydroxide. So again, if you remember your definition for Bronsted-Lowry acids and bases, an acid is going to donate a proton and a base is going to accept a proton. So nitrite here is acting as a base. It is accepting a proton from water to form nitrous acid, and then what is left over once water has donated that proton is you have hydroxide. Okay, so if you have a solution and you have created hydroxide, do you have an acidic solution, a basic solution, or a neutral solution? Well, you have formed some hydroxide, so you have a basic solution. So this salt will give a basic solution. All right, so what we can also see is this is going to tie into our table here. So this is kind of how I logically think through these problems with these salts. But it is handy to have a table here where kind of all of our rules are summarized. So what we have here is we don't have a cation from a strong base and an anion from a strong acid. We do have a cation from a strong base, but our anion is from a weak acid. So here we are in the second row. So our cation is from a strong base. Our anion is from a weak acid. So that means our anion is a weak base, which is just what we saw right here. And so we're going to form a basic solution. That means, of course, our pH is going to be greater than 7. So this is how I work through it logically, but everything is summarized in this table here, which is kind of handy to have. Okay, so that's a lot. Let's make sure there are no questions before I continue on, but let's practice with another salt. Okay, so again, I am keeping up my 4 steps that I use. I'm also keeping up my table, which is quite handy. And now I have another salt. So now I have ammonium, that's perchlorate. So I have ammonium perchlorate. And I need to decide again, does this salt have acid-base properties? And if so, is it going to make an aqueous solution acidic, basic, or is it just going to be neutral? Okay, so again, I'm just going to go through my steps one by one, just like I did with the previous example. So let me switch back to blue here. So my first step again is to dissociate my salt into a cation and anion. Again, this is 2 polyatomic ions. So again, anytime you have a polyatomic ion, you're going to have an ionic bond somewhere. So let's make sure I give myself enough space. So we have ammonium perchlorate, and when I put that in water, I'm going to get the ammonium cation out, and I'm going to get the perchlorate anion out, and that has a -1 charge. Okay, so that is step 1. I've got a cation, I've got an anion. Now I'm going to take each one on its own. So let me first deal with the cation. So we'll first deal with the ammonium cation. Okay, so I'm on to step 2 here. I want to identify again what I call the parent acid or the parent base of each ion. So again, I'm thinking, is there an acid or a base that will form the ammonium cation as a conjugate? And there is. For ammonium, the parent base is ammonia. So when ammonia is in aqueous solution, it will give the ammonium cation and, of course, hydroxide. Okay, so again, here is the ion that I'm going for, the ammonium ion, just like I was looking for. Again, this is a weak base, so I did put it in equilibrium. Now that that's done for the cation, let's also do the anion. So now I have my perchlorate. I keep wanting to call this chlorate, but it's perchlorate. Again, I want to think, is there an acid or a base that will give me perchlorate as a conjugate, either a conjugate acid or a conjugate base? And yes, there is. We have perchloric acid, or sorry, this should be perchlorous acid. And when it is in aqueous solution, it will form the hydronium cation and perchlorate anion. This is also a weak acid, so I put it in equilibrium. Okay, so there are my parent acid and bases of my cation and my anion. And of course, what I've kind of done along the way here is determined if they are from strong acids and bases or weak acids and bases. And you can see both of these are from weak acids and bases, so I've put them both in equilibrium. So then the question is, will these ions have acid-base properties? And to have acid-base properties, they need to be coming from either a weak acid or a weak base. So they each have acid-base properties. Oh, you know what? I'm sorry, I have messed up. So ammonium is yes. But I just realized that perchloric acid actually is a common strong acid. So I am sorry, I have made a mistake there. This is not in equilibrium. This is actually a strong acid. I'm sorry about that. Apparently it's too late in the evening to use my brain. This is a strong acid, so it just goes one way. So the arrow only moves to the right, which means that our anion, our perchlorate, cannot go back to reform our acid. So this anion, our perchlorate anion, is not going to have any acid-base properties. This is why, and maybe, I just don't have that much space on the screen. It is nice to have a table of strong acids and bases handy because, again, just like right now, I totally forgot that perchlorous acid is a strong acid. I was just thinking it was automatically weak. So it's nice to have those somewhere close by to reference. Okay, so now that we've determined the acid and the base, that's the parent, and we've determined if it has acid acidic or basic properties, we need to determine if we're going to form an acidic solution, a basic solution, or a neutral solution. So let's go to our table here. Since we did this at the end last time, we'll do this at the first for this problem. And what we've got here is we've got a cation that's coming from a weak base. So here, this one is a cation coming from a weak base and an anion coming from a strong acid. And so yes, this matches our salt that we have here. So our cation is a weak acid. Again, our base is not going to do anything, which is going to give us an acidic solution. Now I'm going to write our equilibrium expression just like I did for our previous salt so you can see why it is acidic. So if we take our ammonium cation in water. So what it is going to do, it is going to donate a proton to water, and I will get ammonia as the other product. So I've got this salt in solution. It is forming the hydronium cation, so therefore it is going to be an acidic solution. Again, just like what our table said, and obviously that is going to have a pH that is less than 7. Okay, any questions? Nope, no questions. All right, so let's move on to our next problem. Okay, so for this salt, we're going to be doing the exact same thing. We're going to go through each of our steps, and we can use our table to help us. So let's first dissociate this into its cation and its anion. So we have ammonium fluoride. And when it dissolves in aqueous solution, we get the ammonium cation and the fluoride anion. Okay, that's great. Now we have identified our cation and our anion. Let's take each in turn and determine our parent acid or our parent base. Now, we just did the ammonium cation, so I won't go into much explanation there, but this, of course, comes from ammonia in water to give the ammonium cation and hydroxide. Again, this is a weak base, so I put it in equilibrium. And for the fluoride anion, this is actually coming from hydrofluoric acid, which is a weak acid. Now what's interesting, and I won't go into the explanation right now, but hydrofluoric acid is the only halogen that's going to give you a weak acid. So hydrochloric, hydrobromic, hydroiodic are all strong acids, but hydrofluoric is not. So where am I? There's the hydronium ion and the fluoride anion. So this one is also in equilibrium. So this example, I have both the cation and the anion that are both coming from weak acids and weak bases. Okay, so what that means is they both are going to have acid-base properties. So let me just write a yes for both of these right here. And now we need to determine again, is this going to give an acidic, basic, or neutral solution? So I have a cation and an anion coming from weak. So it's not the first row, it's not the third. So we are looking at our very last row here. So our cation is coming from a weak base, our anion is coming from a weak acid. So what this means is we need to know our Kas and our Kbs, because you can see in this space right here how strong of an acid or how strong of a base we're working with is going to determine our pH. So if our Ka is larger than our Kb, then we will form an acidic solution. However, if the Kb is bigger than the Ka, we will form a basic solution. And in the case that our Ka equals our Kb, then we will form a neutral solution. So what we need to do is we need to know our Kas and our Kbs for our cation and our anion. And I do have those numbers. So let me just write these down. So our Ka for our ammonium cation is 5.6 times 10 to the negative 10th. And our Kb for our fluoride anion is 1.4 times 10 to the negative 11. So in this case, what we have is we have Ka is greater than Kb. And if we look down here, we see if Ka is greater than Kb, we are going to form an acidic solution. So this will give us an acidic solution. Now, one tip I want to get, just say for getting these Kas and these Kbs. Of course, Google is great, so you can look these up on Google. But also, if you go back to determining the parent acid or the parent base, so finding a Ka or a Kb for ammonia is very easy. And once you know the Kb for ammonia, because you're looking for the Ka for its conjugate, remember that with a conjugate pair, now this only works for conjugate pairs, Kw is equal to Ka times Kb for conjugate pairs. So obviously our Ka for our ammonium cation and our Kb for our fluoride anion are not related by this equation because they are not conjugate pairs. But what this equation allows us to do is to take a known Kb here and calculate a Ka. And the same thing for our fluoride anion. So finding the Ka for hydrofluoric acid is very easy. If you have a textbook, it's probably in a table in the back of your textbook. So being able to find the Kb for the fluoride anion, you can use this equation here if you don't have this fluoride anion's Kb handy. Again, if you're at a test or you just don't have access to Google or to look it up, you can always calculate it very easy by doing this. And then, of course, you can compare your Ka and your Kb and then determine, based here, if you've got an acidic, a basic, or a neutral solution. Okay, this one was a little bit of a difficult problem. I get that because we're dealing with a lot of Kas and Kbs, but hopefully that becomes a little more clear to you. So now that we've just been able to look at salts and determine if they have acid-base properties and then if the solution is either acidic or basic, it's time to jump into solutions with a given concentration and to determine what the pH is. All right, so here is my first problem. What is the pH of a 0.1 molar solution of potassium nitrate? Again, this is very systematic. You can see I have, in this case, I have 5 steps, and I am just going to go through each step for all of these problems. This one is actually really easy, and I'll show you why, but let's actually work through the steps. So the first thing I want to do, just like I did in my previous examples, is I want to identify the cation and the anion. So I'm just going to dissociate the salt here. So for potassium nitrate, that is going to give me the potassium cation and the nitrate anion. All right, so now I want to know, again, just like before, what is the parent acid or the parent base? So I know that these are going to be conjugates of something, but are they coming from strong acids and bases or weak acids and bases? So if I look at potassium, so we did this with, I think this was our first example. This is actually coming from potassium hydroxide. which is a strong base to give potassium and hydroxide anion. And my nitrate is also coming from a strong acid, nitric acid, which, oops, sorry, I want to put water in there. I don't want to forget that. Again, you don't have to do it this way. I like to do it this way because I like to see the hydronium ion. It's just a little more accurate for aqueous solutions. But if you are doing this on a test or homework, you can just dissociate it into a proton and nitrate. So there's my hydronium cation and my nitrate anion. Okay, so what's going on with this that makes it really easy is that I have got the cation from a strong base and the anion from a strong acid, which means neither of these ions have acid-base properties. So I'll even, just like we did before, I'm going to write no for no acid-base properties. That means in aqueous solution, neither the cation nor the anion is going to change the pH. So this means we don't actually have to do a calculation for this problem because this is a salt that gives a neutral solution. So this is a neutral solution, which means our pH is 7. Okay, so I did want to start with the really, really easy one because we don't even need to know the Ka or the K. Well, you can't look up Kas and Kbs for these because they're strong, so they don't have them. So we have a neutral solution and the pH is 7. But, okay, good. I'm glad we've got time because we will go through calculations for salts that are not coming from a strong acid and a strong base. But those are the easy ones, so make sure you don't overlook the easy ones. Okay, so here is my next problem, and I promise this is not a pH of 7. So what I've got is I have, again, a 0.1 molar solution of sodium. This is hypochlorite. And I am given the Ka of hypochlorous acid is 3.5 times 10 to the negative 8. So that already should, get your brain working, hopefully, to say, oh, I've definitely got a weak acid in here somewhere. I'm going to have to use this Ka at some point. And yes, we will use this Ka at some point. All right, so again, I'm just going to go through my steps here. And my first step is to dissociate the salt into a cation and an anion. So I have my sodium hypochlorite, which is going to give me the sodium cation and the hypochlorite anion. Okay, great. So now what I want to do is I want to identify what my conjugates are. So if I look at my sodium, this is exactly like potassium. So my sodium cation is coming from a strong base, this time sodium hydroxide, which gives sodium cations and hydroxide anions. That means sodium, you could call this a spectator ion. It is not contributing to either making the solution acidic or basic, so we can basically just ignore this. Haha, basically. Okay, that was pretty good. Then I have my hypochlorite. And again, you can see the problem actually gave me my acid. So I already know that this is the conjugate base of my hypochlorite. So we can write this whichever way we want. Let's maybe show this in water. And this will be in equilibrium. Right? Okay. All right, so I should maybe, this does not have any properties. This does have acid-base properties. All right, so I am going to take this equilibrium expression and I'm going to write basically the K for it. So depending again, if you're coming from a strong acid or a weak acid or a weak base, you're either writing a Ka or a Kb. In this case, I am going to be writing a Kb. That's why it says either Ka or Kb at this point. because in some cases you're writing a Ka, in some cases you're writing a Kb. All right, so remember when you're writing Ks, it's products over reactants. And because this is a Kb, it means that the concentration of water has already been taken into account, so we do not need to include water in here. So we have products over reactants. Okay, so that is our expression for Kb. All right, so now what we need to do is we need to actually calculate this Kb. So we are given the Ka of our hypochlorous acid, but we actually need the Kb of its conjugate. So just like we said before, remember Kw equals Ka times Kb. So I guess I'll just write this equation in. Kw equals Ka times Kb. Of course, Kw is 1 times 10 to the negative 14th. And that equals our Ka, which we have 10 to the negative 8th times Kb. So again, I just do the algebra. I solve for Kb, and that is 2.9 times 10 to the negative 7th. Okay, so now I have a value for this Kb. So now I'm really just doing an equilibrium problem. I'm doing a weak base equilibrium problem. So I am going to set up an ice table, or some people call it a rice table. Either way, it's the same thing. So I'm going to rewrite my equilibrium equation here. I'm just going to rewrite it over here so I've got a little more space. This again, and hydroxide. All right, so now I need to know my initial amounts here. All right, so this is where this first equation is important to remember. So again, this is not an equilibrium. It just moves to the right because again, we're dealing with soluble salts. So if I have a 0.1 molar solution of my salt, because this is a 1-to-1 stoichiometric ratio, a 1-to-1 stoichiometric ratio, that means I also have a 0.1 molar solution of my hypochlorite. That is just pure stoichiometry. The nice thing is it's 1-to-1, so there's really, you're just multiplying by 1. So this is where this number comes from. So this is how I know that I have a 0.1 molar solution here of my hypochlorite anion. It's actually coming from not only the information that was given to me, but this equation right here. Oops, I didn't mean to make a mark there. Okay, and we ignore water. You don't even have to mess with it, but I don't have any of my hypochlorous acid or hydroxide yet at the start, initially at equilibrium. So now I need to put in my change. So how much is this going to change? Well, I don't know right now how much this is going to change, so I'm going to call it X. Now, it's important to know which way the equilibrium is going to run because I have a forward reaction and I also have a reverse reaction. So this is Le Chatelier's principle. Because I have 0 moles or no concentration here of my products, my reaction is going to run forward. That means I'm going to use up some product, so that is minus X, use up product. I'm going to use up reactant to form product here. So that is why that's a negative X and these are positive X's here. Now I need my equilibrium concentration. So I'm just adding my columns. So this becomes 0.10 minus X. And of course, this is 0 plus X, which I'll just call X over here, which is the same thing there. Okay, so that is my equilibrium table. And now I want to plug it into my expression for Kb, and so that I can actually calculate what the value of X is. So I am using this Kb here. Again, we have the value for Kb. So you know what, I'll just write it as Kb is equal to, I need the concentration of my hypochlorous acid, which is just X, multiplied by my concentration of hydroxide, which again is just X. And all of this over my concentration of hypochlorite, which is 0.1 minus X. And again, Kb I actually have a number for, so I can write the number in over here. And now what I've got is I've got an expression with one variable, so I can solve for X. And this is what we're really going for, is to be able to solve for X. Now what I would like to do is I'd like to drop this minus X here because I really don't want to have to use a quadratic equation. So there are a couple things that we can do to test and see if we can drop this minus X term. So if we assume that X is really, really small, then 0.1 minus X is pretty much just going to be 0.1. So you can use what's called the 500 rule. And what this is your initial concentration, in this case of base, my initial concentration of base over my value for Kb. If it is greater than 500, then I can drop that minus X. So let's put these numbers in and let's see if we can do this. So my initial concentration of base is 0.1 molar. And of course, I have my Kb here, 10 to the negative 7th. And that is 3.5 times 10 to the 5th. Okay, that, yes, is definitely greater than 500. That is a true statement. So what it means is I can just drop that minus X, and then this makes this quadratic so much easier to solve for because all I have is an X squared term. How are we doing on time? Okay, because we're running a little late on time, I am going to do just one simplification here and let you guys work through the algebra. So this simplifies to X squared over 0.10, which means that X equals 1.7 times 10 to the negative 4th. Okay, great. We found what X is. So what does that do for us? All right, so let's go back and remember what X is. So what is X? So if we go back to our equilibrium table, you say, okay, so X is the change, but that means that X is the concentration of hydroxide. So if I know the concentration of hydroxide, I know that it's going to take me a couple steps, but I can eventually get to pH, right? So what I'm going to do now is I am going to calculate, okay, so you can do this a couple different ways. I'll show you how I like to do it. I'm actually going to calculate pOH. So I'm just going to take the negative log of this X concentration. Again, it's the concentration of hydroxide. So my pOH for this solution is 3.77. But since the problem wanted pH, I have to convert that. So remember that, I'm kind of running out of space here. Let me put it over here. 14 is equal to pH plus pOH. So 14 is equal to pH plus 3.77. So that means my pH is 10.23. Okay, that is all the way at the bottom. So I am just going to highlight that by putting a box around it. And this also makes just logical sense, right? Because I've got a weak base in solution, so my pH should be greater than 7, right? So hopefully if you got to this point and you calculated your pOH and you weren't maybe really paying attention and you thought you calculated your pH, hopefully your logic brain would kick in and say, wait a second, if I have a base, then shouldn't my pH be greater than 7? And then hopefully you'd go back and go, oh, I actually calculated pOH. So our pH here is definitely in the basic range. It's greater than 7. And we've actually taken a salt and we've made a pretty basic solution from it. Okay, any questions? Daytona 500. Thanks, OG Benchmarks. All right, so let's get through. I think we're just going to get through one more problem here, which is totally fine. You can see these problems do take a while. All right, so we've got ammonium bromide in this case. Again, I am using my steps here, my 1 through 5 steps. So first, I'm just going to dissociate the salt into its cation and anion. So we have ammonium bromide will give me the ammonium cation and the bromide anion. Okay, so now I need to decide what these guys are coming from. What are they conjugates of? We've seen ammonium. I think this is now maybe our 3rd time of seeing ammonium. So you already know that ammonium is coming from ammonia. So again, if ammonia in water is going to give ammonium and hydroxide. Okay. All right. And our bromide anion here, this is actually coming from hydrobromic acid, which is a strong acid. You guys already know what this means. It means that the bromide anion is not going to do the reverse reaction, so it is not going to contribute to acid-base properties. Okay, so this one will, yes. This one won't, no. All right, so again, we don't have to worry about bromide, just like in the previous problem. Just like we just kind of ignored the sodium, we're pretty much going to ignore the bromide anion in this case because it's not contributing to anything. All right. Now we need to write either our Ka or our Kb for our conjugate. So in this case, we have the ammonium cation. So here is our equilibrium. So this in water, again, it is weak. It is going to form the hydronium cation and ammonia. So it donates a proton to water. So now I can write, in this case, the Ka. So this is an acid. This time I'm writing a Ka, whereas last time I was writing a Kb. So my Ka for this weak acid, again, products over reactants, and water is already folded into Ka. So I have my hydronium cation and my ammonia, and that is over my ammonium cation. All right, great. So now, just like before, I want a value for this Ka. Now, the problem did give me the Kb for ammonia. It is the conjugate of ammonium, so I can use my Kw equals Ka times Kb to determine what my Ka is. So this is 1 times 10 to the negative 14th times my Ka, and I am given my Kb up here. So that is where this number is coming from. And I get a Ka of, let's see, I've done this calculation. Here it is. 5.6 times 10 to the negative 10th. Okay, so hopefully you can see I'm doing very much the same steps that I was before, even though now I'm dealing with an acid instead of a base. We're still doing very logical, very systematic steps. Okay, so now what we want to do is we want to set up our equilibrium. So I'm going to come over here again. I'm just going to rewrite my equation. And I'm setting up my ice table, or again, rice table, however you want to think about it. And ammonia. Let me fix that. All right. So I need my initial concentrations, and the problem gives me my initial concentration of my salt. Again, remember that I've got this first equation here. So my salt dissociates. That means for any moles that I have of my salt, I'm going to get 1 mole of my cation. So because I have a 0.1 molar solution of my salt, I have a 0.1 molar solution of my ammonium cation. Again, this is just pure stoichiometry. So this is 0.10. And of course, I don't have any hydronium or ammonia, and we just ignore water as usual. So now I need my change. And just like before, I don't know what my change is going to be, so I'm going to call it X, but I know my equilibrium is going to push to the right because I have no products right now. So this is a minus X, X, and X. And now I can get my equilibrium concentrations just by adding down my column. So this is 0.10 minus X, and these concentrations are simply X. All right, so now I want to plug these into my Ka. So my Ka is going to be the concentration of hydronium ion, which is simply X, times my concentration of ammonia, which again is X, divided by my concentration of ammonium, which is 0.1 minus X. Now, just like before, I really want to be able to drop this minus X because it means I don't have to use the quadratic formula, and it just simplifies the equation so much. So let's do our little side calculation, and let's see if it passes our 500 rule. So in this case, because I have an acid, my 500 rule is simply my initial concentration of my acid over my Ka, which I have. So this is 0.1 divided by my Ka, which is 5.6 times 10 to the negative 10th. Sorry, this should be greater than 500. And what I get is 1.7 times 10 to the 8th, which is definitely bigger than 500. So check, yes, I can drop this minus X, which just makes my calculation so much easier. So if I come back over here to my last little space here, what I've got so far is I've got my Ka, I've got my 5.6 times 10 to the negative 10th, and I'm just pulling from this expression here, is equal to X squared over 0.10. Because, I'll just write this here, I can drop this minus X. Sometimes you can't drop the minus X, but I'm always glad when you can. So this means that solving for X becomes very, very easy. And so X equals 7.5 times 10 to the negative 6. Again, at this point, I really want to be thinking, again, now wait, what is X? So I've spent all this time and effort finding what X is, but what does X mean? Because we're not just in math class, we're in chemistry class, so X has a meaning. So this is where I go back to my equilibrium table, and I remember that X is my concentration of hydronium. X is also my concentration of ammonia, but I'm really focused in on hydronium because if I take the negative log of my concentration of hydronium, then I get pH, which is exactly what the problem wanted. Okay. So pH is equal to negative log of hydronium, which is my value for X. And so my pH for this salt is 5.1. Again, hopefully this makes sense. You have a pH that is less than 7 because you have a very weak acid in solution, so it should give you a pH of less than 7. Now this is not strongly acidic, but still it's acidic. That's all you need to know. And wow, okay, we are almost at 8 o'clock. There is one more thing that I wanted to show on this problem that I didn't show on the last one. But so we assumed that we could take this minus x term off. And once you have calculated x, you can do a second check just to make sure that your assumption is valid. And it's a little bit more robust check. It's called the 5% rule, which you might know. And what you're going to do is you're going to take your value of x divided by your initial concentration, again, of acid in this case because we had an acid, and multiply that by 100%. Now, that should be less than 5%. If it's less than 5%, then your assumption was valid. If it's not less than 5%, if it's greater than 5%, then you actually need to go back and calculate what x is using the quadratic formula. Okay, so let's plug these numbers in for us. I'm going to have to write a little bit small. So we have our value of x over our initial concentration of acid times 100%. And that is actually 0.0075%, which, yes, is definitely less than 5%. So our assumption is valid. Let me get that out of the way. Our assumption is valid. It means that we did the problem correctly and we didn't need to take x into account. But I thought I would just throw that in so you have two tools to determine if you can drop that minus x term. The 500 rule is an easy way to do it before you've gone through all the calculation. But once you've gone through the calculation, assuming you're not on a test and you're crunched for time, it's nice to check the 5% rule and just make sure that your assumption is correct. Okay, so looks like there are no questions, at least not now. I hope you found that helpful for finding the acid-base properties of salts. And next Wednesday, we will be doing another live stream. So if you have a request for topics or problems that you want worked, please feel free to email me. It's just Karen@chemhelpasap.com. And I also do tutoring if you feel like you need some one-on-one help. And thanks so much for joining us. Good night. Bye.